Welcome to Ada University. I'm Quentin Osham, and today I'm going to introduce to you the basic Ada type system. Let's get started. I will be assuming that you are familiar with the very first lessons of the overview course. However, since this is the first formal lesson of the basic course, let me start by introducing some syntactical information. Ada is a case-insensitive language, which means that identifiers are the same if they are written in lowercase, uppercase, or mixed case. This doesn't mean that the recommendation is to use random casing for identifiers, but rather that a new identifier should not be created on the ground that the casing is different, which should avoid a number of programming mistakes. Identifiers always start with a letter and may end with a letter or a number. Underscores characters are allowed as long as they are surrounded by letters and numbers. That is to say, you cannot have two consecutive underscores in the same identifier. So let's start with a little question. Which of the following identifiers are legal? Just check those that will compile and hit submit. There are only two identifiers that are legal here, something and A679. My ID is not, because it has two consecutive underscores. Hello starts with an underscore. The only thing that can start an identifier in Ada is a letter, which is why constant is refused, as well as O9A2. Yup is illegal here because it finishes with an underscore instead of a number or a letter. Ada commands are written with two dash followed by a comment that will be written up until the end of the line. This is equivalent to the C++ dash dash end of line commands. Note that in Ada there is no block comment as you would have in Java or C++. Numbers can be expressed as with any other language, but Ada provides additional capabilities to the way to express numbers. The first one is the possibility of having underscore in a number, which can help separating group of digits. If you look at the example on the screen, the left example makes it clear that I'm talking about 1 million. The right one is much less readable. As for many other languages, it is possible to express a number according to its base, base 10 being the default, but all bases from 2 to 16 are allowed, and the syntax is base dash value dash. For floating point value, floating point literal need to have a decimal part. So 1.0 is a floating point literal, 1 is not. To declare a variable in Ada, you will write the name of the variable, followed by a colon, followed by the type. So, if you will, it's the other way around compared to languages such as C, C++, or Java, where the type comes first and then the name. It is possible to have initialization at declaration time Here, for example, I'm saying that B is initialized with 5. Constant can be declared with the constant modifier coming right before the type name. In the case of a constant, an initialization is required. In Ada, it is possible to declare several variables at the same declaration point, and if this declaration point has a default value or a default expression, this default expression will be evaluated separately for every single variable. So here I have DE equals f of 5. Even though f of 5 is written only once, it will be called twice, once for D, once for E, exactly how it would be the case for the C example on the right. Elaboration of variables is done sequentially. This means that you cannot refer to a variable before it has been declared. So here I'm trying to access to D before it is created, and that will result in a compilation error. One last note. Although I'm using the assignment symbol in these examples, what I'm redoing is called an initialization. The properties of assignment and initialization are slightly different. We will see the details in further lessons. Now that we are done with this initial discussion, let's talk about typing, and in particular the simple types in Ada. Ada is a strongly typed language. This is probably one of the main differences with languages such as C++ or Java. So there is a clear distinction between the semantic of a type, its meaning, its purpose, and its representation in memory. One of the most common examples is the notion of kilometers versus miles. Those two notions are incompatible. It does not make sense to add a number in miles to a number in kilometers. With most languages, it is very hard to represent this incompatibility. With Ada, those would be two different types, and by default, mixing those two types would be forbidden, except with explicit conversions. In Ada, all types are named and associated with extra properties, attributes, ranges, size, etc., etc. Implicit conversions are forbidden. For example, a floating point value is something very different from an integer value, and actually converting a floating point to an integer has a lot of consequences. Many languages allow to do this operation implicitly when you need to mix two values of those two types. It is going to be forbidden in Ada, and the developer will have to explicitly convert either the floating point to integer or the integer to float. As a matter of fact, as you can see on this example, doing one or the other has a clear impact on the result of the computation. This is another view of the Ada type model. On the left hand, you will find all of the simple types, or elementary types, containing in particular numbers. On the right hand side, all composite types, that is to say, types that are composed of fields or components. For now, we are going to concentrate on 3 categories of types. All of this will be elementary type, and actually elementary scalar types. We are going to look at enumerations, signed integers, and floating point types. So scalar types are single value types. They are divided in 2 categories. One is called the discrete type. A discrete type is a type that can be enumerated, that has a finite number of values. So there is no notion of precision. And basically, discrete types are integers and enumerations. It is defined as opposed to continuous types, which are mapping real numbers, so floating point types, for example. And these continuous types are related to the precision. Some of those scalar types are associated with numerical operations, plus, divided by, etc. We will list those a little bit later. The Ada standards provide some default types for signed integers, enumeration, and floating points. The integer that you will use the most is actually called integer. Short integer, long integer, long integer are available as well. Although if you come to need some specific integer, for example in terms of data range, it will be better to define your own, as we will see later on. One important point here is that the Ada standard does not provide any guarantee in terms of how big those types are. The only thing that we know is that short integer is smaller or equal to integer, which is smaller or equal to long integer, etc., etc. But on certain implementation, all of these types might be implemented on 8 bits. In terms of enumerations, the 2 main default enumerations that are available are character and Boolean, as you might expect. For floating point types, it's pretty much as for signed integer. You will have access to a range of default floating point type: short float, float, long float, long float. But again, if you are relying on some specific data range or precision, it will be better to create a custom floating point number. Most of the time, you will find that the default type provided by the system don't quite fit what you need. So it's very handy to be able to define your own type and provide it with your own intent and semantic. To define your own signed integer type, for example, you will create a type declaration and then complete it with a range definition. So here, for example, I am creating a first type that is called score, and I'm specifying that the acceptable values for this type go from 0 to 20. I am declaring a second type, percentage, that is going to be used in a different context, and for this second type, the range of valid values go from minus 100 to 100. The compiler will check that it can represent this type using the processor that it's targeting. So for example, if I want to create a very big type, but I only have access to a small processor with like an 8-bit or 16-bit units, the compiler will be able to flag that and refuse to compile a request that is not doable. To declare an enumeration type, I will need to again create a type declaration and then define it by a list of literal. So here, for example, the type color is defined by 5 values and the type ternary is defined by 3 values. To define a custom floating point number, what I'm going to provide is the minimum requested precision. Here, for example, I am requesting the type distance to be at least of 10 decimal significant digits. If it is possible to compile such a type on the system, it will work fine. But if I'm requesting a precision that is too high, the compiler will flag that and refuse to compile. It is possible to specify as well a range of valid values for a floating point type. Just one word of warning, as introducing these range checks will decrease largely the performances of floating point computation. So it may not be a good idea to do that. Depends on the usage of the type. This note only applies to floating point types. It is perfectly fine to have ranges for integer types. Types that were presented in the previous slide were brand new types. But in a lot of situations, you will find that there is already a type implementation that you would like to reuse to create your new type. So it is perfectly possible to define a new type according to an old one. Here, for example, I'm saying that math core is a new type based on the implementation of score. Math score and score are two completely independent types, but they share the same implementation. In addition to that, when creating a new type, if it's an integer type, it will be possible to reduce the range of values. So for example, I always been very bad in math. So it's structurally impossible to me to get above the average grade, which is 10. So I'm just creating this new type math core, and I'm declaring it as being of a range from 0 to 10, which is a smaller range than the one of score. And I could do that with pretty much any discrete type. For example, here I have a type primary color, which is based on the implementation of color, but just accepts values from red to blue. Although it is impossible to mix different types by default, if they share commonalities in terms of implementation, it will be possible to make explicit conversions. Here, for example, I have v1 and v2. v1 is of type float, and the compiler knows how to convert a floating point value to an integer. So I can convert it by writing the name of the type and then the value in parentheses. Note that conversion may introduce an additional verification, a check. Here I have v1 and v2, which are of two types that are integers typed. So although I cannot mix them up, I will be able to convert one into the other. However, the valid range of value is different. And if v1 equals 0, when I convert v1 in the type t2, which does not accept the value 0, I will have a runtime error, an exception, and the program will stop. Signed integers and floating point types share a lot of operators in common. Basically, all the common arithmetic operators are available. Note that the comparison, the inequality in particular, is different in Ada than for languages such as C++ or Java. It's /equal instead of !equal. Signed integer types have two additional operators, mod and rem. Both of them compute the modulus of an integer number. The difference is that when computing the modulus of a negative number, mod will look at the closest positive number, while rem will look at the closest negative number. Let's now introduce attributes. Attributes are really useful in Ada. They are properties of Ada entities that could be a variable, a subprogram, and of course a type. You probably know already about the image and value attribute that converts back and forth a value to a string. Depending on the category of the type, you will have access to different attributes. Let's have a look at a few examples. This is a list of attributes that are common to all scalar types. For example, first we'll provide the smallest value that can be represented on this type, and last we'll provide the biggest value. Image and value, we talked about this, that converts a string to a value back and forth, and this is available for all types, for all scalar types. Min and max will return conveniently the minimum or maximum between two values, and pred and suc will return the previous value or the successor, the next value. What's interesting here is that this notion of previous or next value is available for floating point number as well, and of course it will take into account the number of significant digits to compute the previous or next value available. Range is an interesting attribute that you will see a lot as well later on when we talk about arrays, and it's an equivalent of first ... last. Discrete types have two interesting attributes, pos and val. Pos will take a value in parameter and return the position of the value in the list of value. Val will do the other way around. It will create a value according to a position. There is an example of usage here where I want to retrieve the first character, so I use the position 0, and then I want to get the one character next to it, so I'm retrieving the position, adding 1, and then converting back to a value. Of course, to do this very thing, I can use pred and suc that has been presented in the previous slide, but there are situations where those two attributes makes a lot of sense. Finally, here is a list of attributes that are specific to floating point values. You will find all means to convert a floating point value to its closest integer value by truncating it, rounding it, getting the floor, the ceiling. One very important information here with regards to conversion from floating point value to integer. A lot of languages are implementing this through truncation. However, with Ada, it's rounding that is used. So, in other words, the expectations that you will have in C in terms of conversion between float to integer will be invalid in Ada. Let's now verify your understanding with a quiz session. For this question and the next, if you think that there are no errors in the code, click on the green icon next to the yes. If you think that there are errors, click on the location of those errors in the code and then hit submit. There is an error on this slide. I am trying to declare twice the same variable, so the second declaration is a compilation error. The compiler will verify that the requirement I have on a new type can be implemented on the target architecture. This type goes from -2 power 256 to 2 power 256. It is very unlikely that any architecture will support this range of values. So, in all likeliness, the compiler will refuse to compile this type because it cannot be represented. This is a perfectly vanilla declaration. There is no trap here, no error. Although style-wise, this is not very good, and I will probably have some coding rules and coding checker that will refuse the different casing between the classroom declaration and the classroom reference. From the Ada language point of view, there is no error here. Ada allows me to restrict the range of a given type, which I'm doing on T1. However, I cannot extend this range when declaring a new type. So T1 is between -10 and 10, and I cannot create a T2 based on the implementation of T1 with a larger range. This is perfectly correct. The successor of the floating point number 0.9 is going to be computed according to its precision. What I'm doing here is first to convert the floating point value 7.6 into an integer. I am doing a rounding here, so this conversion is equal to 8. I am then doing a division between 8 and 10, and what I'm doing is an integer division. So on most machines, this division is doing a truncation. The result of the floating division would be 0.8. So the actual result of this integer division is 0. I am then converting this to a floating point value 0.0. This is a very typical mix-up between val and value. Val takes a position and creates a value out of it. Value takes a string and creates a value out of it. So here what I would need to do is to replace val by value and value by val. These calls are perfectly fine. The first two are expectable. Ada is case insensitive, so capital A and lowercase a are equivalent. And the last one is a nice flexibility of the value attribute, which automatically trims extra spaces. This type definition is peculiar. Indeed, the range of t goes from 1 to 0. So far we've only seen incrementing ranges, for good reasons. Ada always expects the range value to be given in a growing number. So what this created is a type that has no valid value. However, this is legal, and it is legal to declare a variable of that type as well. Of course, the minute I am assigning a value to this variable, I'm going to have an exception. There are situations where this construction is quite useful. We will see that later on. This wraps up the first lesson of the Ada basics. I hope that you enjoyed it. Stay tuned, there is much more to come.